Good morning, students. Welcome to the first lecture in advanced networking. Hope I'm audible clearly. Today's lecture will be an introductory one. We will talk about the various topic areas that we will be discussing in the latter part of the course throughout the semester. And towards the end, I will also discuss about the continuous assessments, lab activities, examinations, and all the other relevant things as well. So we'll discuss about those towards the end of the lesson today. So first we'll start with the introduction and then we'll get to that. So, advanced networking course is largely based on the version 6 of CCNA routing and switching essentials, and most of the content is directly taken from that. So this is not essentially a one-on-one mapping with the CCNA content, or at least at this stage, we don't have any particular plans for delivering it in that manner, but we will cover most of the key aspects that are relevant to that, and number of students have gone on to doing like examinations based on this and other practices and things like that, but at least at this stage that is not our major focus. But given there is a high preference for that knowledge area in the industry, we have adapted that as sort of a basis for that. And also we have, as a faculty and as the department, we have an agreement with Cisco, and we have signed up as a Cisco Academy. So some of the things that you will be able to do as part of that would be, again, I'll talk about the lab activities toward the end, but some of your lab activities will be directly based on that as well, which will be done by a different lecturer this time. So let's start with discussing about routing concepts. So you would have covered some aspects of routing in the previous courses. You would have some understanding about routing. And in this course, we will go further and explore that area and discuss about various related topics, and get a more in-depth understanding about routing and switching. So when we talk about networks, when we talk about sort of the characteristics of networks, we can define the networks based on a number of, or we can discuss about networks based on a number of different characteristics. And one of the major aspects why understanding this would be relevant is because networks can be used for various different applications or various different uses, and different users will have different requirements and different needs from the network. Say, for example, if you are accessing normal websites, for example, or basic web applications, uh, the network requirements for that would be significantly different if we are using things like interactive gaming or video conferencing. There, the requirements would be significantly different. Then if you think about something like e-commerce, again, the requirements would be significantly different because there the focus may be quite different, maybe focusing on security, and those aspects would become much more important compared to the others. So overall, we can define a number of key characteristics that we would like when we discuss about a particular network. So the first one is topology. This is something that you would be familiar with from your previous courses. So this is where we can talk about one, the physical topology, and two, the logical topology. So the physical topology is how the network devices, the endpoints, and all the structured cabling is physically structured. What are the physical connections between the devices that are participating in the network? Compared to physical topology, logical topology is mainly about how these network devices are actually interconnected from the user's point of view, because these two doesn't always have to be the same, because there can be a particular physical topology, but logically the network can be structured somewhat differently from the physical topology to the end user who is actually participating in the network. So that type of option is also available within these in networks. Then another key characteristics that a lot of us would be familiar with is the speed of the network. So that is, what is the speed data transfer can happen through a given link between an endpoint or another device, or between two devices within the network. Cost can be again a significant factor, because when we build a large networks, when we think about enterprise scale networks, price of components would significantly contribute to the overall cost of the network, both for installation cost and can sometimes even contribute to the maintenance cost of the network. So this will have to be considered, particularly if we are looking for other characteristics like speed, for example. Sometimes we will have to compromise speed to get a better cost calculation for the overall network. Or if speed is essential, we may have to go up in cost. So those are some trade-offs between these characteristics that we will come to. Then some of the other ones that we will consider are around security. So again, how protected the network is from external actors and external actors coming in, and what happens to data in transmit between two devices. Can somebody get to that data, and can they steal information, or can they participate in the network without authorization? So these are some of the things that we will talk about in security. Then things like availability, scalability, and reliability. Again, these ones would also be impacting on networks, because availability is that we are able to use the network when we want to use the network. Scalability is when we have a network and it needs to accommodate more users at certain points in time and less users at other times. So these are like things when we have these peak hour needs. Say, for example, with our Zoom network, the local Sri Lankan, the Learn Zoom data center, because we go through that data center for these sessions, and it has certain issues related to peak hour performance because there's quite a lot of peak performance around 8 to 10 in the morning, like that. So and whereas like then there are other hours where it's not utilized a lot. So how it can scale up to accommodate more users around certain periods of time when there's more need. So that's around scalability. And then reliability is again how much we can depend on the various components that are participating in the network. So we will have quite a lot of different components like switches, routers, and other cabling aspects, data transmission devices. So quite a lot of devices, and all of these devices together make up a network. So even if some of them fail, it could impact the overall network. So we should have reliability and sort of dependable network components across the network. So when we think about connecting to networks, uh, there are a number of ways that we may connect to a network, or the networks can be structured in a number of different ways. Say, if we think about a scenario of a home office, for example. So in a home office environment, the way that we may would be fairly simple. So this is something that you would be familiar with, and I would assume most of you would be connected in a manner similar to this. So you may have a device, a single device that would function as the router, the switch, and possibly the wireless access point, and to which you may be connected if you're on a laptop or a mobile device that may be connected via a wireless access point. And you may sometimes have additional devices like a printer or something that may connect through a wired connection, or sometimes you may have a computing device that also connects through a wired connection. But that is generally a normal connectivity option that we would have in a home or even a small office environment. And then from that common routing, switching, wireless access point device, we will connect to the internet service provider. So that would be the internet service provider router as well. So that is a typical way that we would connect devices from a home network, a home office, or even a small business scenario that can be sort of commonplace, that can be possible. So then if we think about certain other environments, say if we have somewhat of a larger office, there it may be possible to have a bit more number of devices. So here what we may have is, like, say we may get connectivity from the internet service provider, and we will have a router there from the internet service provider. And beyond that, we may have additional networking components within the organization. So we may have switches, wireless access points. So it is possible to have some of these other additional devices in such an environment. So then in terms of endpoint devices, again, we can have laptops and mobile phones connecting through wireless networks. We can have certain endpoint devices and voice over IP phones and things like that connecting through wired networks. And it's possible to have other shared printers and things like that also within on-premise servers and things like that, again connecting through wired network. Then all of these things are combined together at the router point and pushed out of the connection is then to the internet service provider. So that is in a sort of a fairly sizable office environment or enterprise environment. Then what we can have is, if we think of this organization as not a standalone organization, but it is a branch organization of some other large enterprise, it is also possible this branch organization connects back to the large organization's internal network or to their private network. So there what may happen is that edge router at the branch office, in addition to connecting to the internet service provider, would also connect to the head office of the organization through a wide area network. So it will connect, it will establish a private connectivity to the head office as well. Then when we think about that head office type of a scenario, there we may have even more complex network setups. For example, we could have fiber optic cables providing the Ethernet backbone. We could have layer 3 multi-layer switches connecting in between and having sort of a structure of redundant switches. So there's always a failover option. We could have additional corporate servers and other devices in the environment. And again, from here also we can have additional wide area network connections as well. So some of these differences we will actually revisit in a latter part of this course, and we will also discuss this even further in the course that would be coming in the next semester as well. So now the question is, so once we have such a networking landscape, why do we need routing? So what is the necessity for us to do routing? What is the main thing that we achieve by doing routing? So routing is essentially there to interconnect two networks. So that is the main purpose of routing. So if we have, say, in this example, we at least have can identify first networks in these three the environment. So there's one network at home, one network at this office, and one network at this branch office. So there are 3 separate networks here. So with these 3 networks, how do we go about interconnecting these networks and so that the devices within each of these networks can talk to each other? Because otherwise these devices don't know how to talk to some of these other devices. Because for example, the scenario could be someone from the branch office needs to connect someone from the head office. So then how do they know how to connect? So this is where the aspect of routing comes in, where these devices will learn about other possible networks that they can connect to, and they will find a suitable path to reach to those devices. Say, for example, if we are to connect from branch to the central office, it may be that we connect through path like this. That may be one option to connect. So in this case, that is the one that we could see. And then these routers will keep this information in a data structure called a routing table. So they will store this information in a data structure called routing tables, and that is what would be used. That is what would be used to make any interconnections between these separate networks. So when we think about routers are essentially computing devices. So they are essentially some form of computing devices, and it is even possible for us to use even a typical personal computing device as a router if we have the right software running on that computing device. Because at the end of the day, it is even in typical routers, they will have the standard computing components such as the hardware components of CPU, memory, some storage and things like that, and some software and operating system environment and some other additional firmware or software that is performing the routing activities. So that is essentially what a router is. The main sort of difference from a router to a personal computer, for example, is that they need to have certain specialized ports and network interfaces to interconnect to other networks. So to establish those network connectivities, we may need to have additional network interface cards attached to that computing device. And once we have that, we can essentially that computing device essentially becomes a router with all the hardware and software components. So this is actually something that you could look into, because there are various ways, various operating system options, software options that you can do and try out setting up your own routers in a typical personal computing device. That's a possibility as well. Moving on, then when we think about routers, as we said, the main responsibility of the routers is interconnecting networks and forwarding information, forwarding packets from the source networks to the destination networks through whatever the suitable path that they can find. And when a router needs to connect to different networks, then it will need multiple interfaces to connect to the different networks that it is interconnecting to. For example, if we take the scenario of the home router, that one is only connecting to the internet service provider. So it is making a single connection to the internet service provider. So you can everything else as another network. So that is one network, and everything else it will consider as another network. So everything else it is connecting to. Whereas if we think about the branch or the central office scenarios, they make at least two connections. They make a connection to the internet service provider directly, so that would be one network that they are connecting to, but they are also connecting between themselves through a private connection through a cloud service provider or whatever. So there it becomes another connection, another connectivity. So they are connecting to two different networks. They are connecting to the internet service provider network, but they are also connecting to their organizational network. So they will have to have two different interfaces connecting to these two different IP networks. And then when a request comes from, say, one of these devices within the organization, if it needs to go to, say, a device at the head office, for example, then if this is what needs to happen, it will arrive at the router, and the router will determine which is the best path to go. So it will go through this router and reach this device. On the other hand, if the communication is from one of the internal devices to the device at that home office, so then it will come to the router and it will determine it would be the other suitable to reach to the other network. So it will go through that network towards the final destination. So that is how the basic interconnectivity action of routers will happen. The next important task a router would perform is about choosing the best path. So again, in most network connectivity environments, it would be possible to find multiple pathways to reach a particular destination. So in that case, router would function as the point where the decision is made about what is the best path to reach the destination from the source. So it will examine the packet that it receives, and it will look at what is the destination the packet needs to go to. Then it will look at the routing table information, and based on that it will determine what is the best path and what is the next point where it should send the packet to. So it will essentially function as a map for the overall network in terms of deciding this aspect. So we will actually discuss about this aspect of routing in much more detail in upcoming lessons. Then to do this routing activity, the routers need to have some mechanism of what is known as packet forwarding. So when packets are received at the router, they need to make some decision in terms of how they forward the packet, because they are going to receive a large number of packets at the same time concurrently. So they will have to have enough processing power and capability to process all these packets and make decisions in terms of deciding where packets can be forwarded to. So again, there are a number of mechanisms to do this, and again we will discuss many of these in more detail later in the course. But there are a few different approaches to do this. One of the simpler mechanisms is known as process switching. What happens is all the packets that come into the router are taken into the router's control plane, and if each packet is analyzed, a new decision is made as to where it should go to, and then they are sent out through the correct network. This is a simpler approach and was one of the oldest ways of doing routing, but this has become very inefficient and not so suited in the modern network era because it can be very slow, because each of the packets needs to be checked and matched to a particular destination and all that. So this is no longer the norm in most high-end routing needs. If we have our needs are high, it can still be used if the needs are not that high, but other places we may have other alternative options. So one of the alternative options we have for packet forwarding is what we identify as fast switching. So it is again a similar approach. So if a packet comes in, it goes to the control plane and a decision is made of last packet. Once the decision is made, that information will be stored in a cache environment that we will have. So now the advantage is, if we get another packet that comes in, and if that packet matches an entry in cache, we can directly use that information for the packet. So if there's a match, we will use the cache. If it is no match, then we'll have to go through the control plane. So this becomes a much more efficient process compared to process switching. So that is, fast switching is comparatively better than process switching. Then there are more sophisticated implementations of switching mechanisms, packet forwarding mechanisms, that is, and there are a number of proprietary versions of such packet forwarding mechanisms. One of that is Cisco Express Forwarding, or CEF, and it is a variant of, or it is somewhat similar to the fast switching approach, but then it has additional capabilities in terms of so it has the forwarding information similar to what we have in the fast switching environment, but it also uses an adjacency table. So here what happens is, if something happens in the network environment, so if the network environment changes, if there's the change in the network topology, that change is quickly added into this. So the tables are updated. So the problem with fast switching is, if something happens in the network environment outside, that information is not immediately reflected in the cache tables. Whereas in this environment, that knowledge is shared back into this place, and the forwarding information base is recalculated, the lookups are performed again, and that information is kept up to date. So there's the all the packet forwarding can continue to happen through this quick express forwarding mechanism. So we will actually again look at some of these packet forwarding approaches in much more detail later on in the course. Then we have the concept of default gateways. So when we say a default gateway, it is essentially say when we think about uh, forwarding packets between networks, we should have a, a place where we want to forward those packets to. Because, for example, if somebody needs to reach one of these devices from an outside network, so then that information needs to come through this router, and information to that router is going to come to this router. Say if the information is coming from this end. So at this router's point, it will not have any information about these devices. So it doesn't have any information about these devices. It can only have information about this router. So it can have information about other routers. So then what needs to happen is anything that needs to go to these devices, the determination should be it should be sent to this network. So that common entry point to that network, which is this router, is what we would identify as a default gateway. So the default gateway is the device that connects the local network to remote networks, and any connections into the local network will come through that default gateway. So normally routers are configured as default gateways in a network. In and out of the network, if we have different networks, we can have multiple default gateways and so on. So that is like the default entry point into the network. So then when we think about networking and network addressing and all these things, we can document our network with a number of different information. So say if we take this network as an example, we have a number of different devices in the network. So we have a number of different devices. And between devices, they can use different interfaces, that is, different physical interfaces interconnecting between these devices. They can have Ethernet connectivity, they can have fast Ethernet. There can be different interface types interconnecting between these devices. Then each of these devices can have separate IP addresses assigned to each of these devices and corresponding subnet masks. So IP addresses and subnet masks are also possible. Then for edge devices, they will also have their corresponding gateway. Say for example, if we take this PC as an example, it will have a physical connection to this switch. So in addition to the that is the interface that it is connecting, it will have a IP address allocation it will have a subnet, and it will also have a default gateway that it connects to. So we can document this information in two. Typically, we will document such information in two forms. One is as a topology diagram, so that is the diagram above, or as a addressing table, so that is like the table below, where all this information is recorded for our understanding of the network. So when we start to work on networks, or when we start to plan on building networks, this is essentially one of the starting points where we would start with. So we will start the plan for our network with such a document, either a topology diagram or an addressing table, and most of the time both. We may have both of those information together to better understand the network before we actually go into implementing the network. So now, if we look at the aspect of each of these properties of different devices, one of the key one is the IP address of devices, because all the devices will have to have IP addresses. And in the case of host devices, um, this IP address for host devices can be either assigned statically or dynamically. Again, this is something that you may have an understanding from the previous courses, and we will actually discuss this in much further detail later in this course as well. But the main idea is, if we have a device, if we have a computer, a mobile device, or anything that is connecting to a network, we can assign an IP address, a subnet mask, default gateway, and all these information manually. So this is something that you would be familiar if you have done that on a PC, for example, on a Windows PC or anything. You have gone into IP configuration and you have put the IP address, subnet mask, and all this information manually. So that is one possibility. But one of the most common ways that we would do this in most networks is using a dynamic approach. So the users don't have to manually configure this information. Once the connectivity to the network is established, this information can be obtained from a DHCP server or a dynamic host configuration protocol, that is DHCP server, and it can provide the IP address, subnet mask, default gateway, and all this information, including DNS server informations, to these devices. So most host devices these days that we would encounter would use DHCP. So most of your phones and laptops and all that you would use in your home networks, or even if you bring it into the university network and all, you are most likely to use DHCP rather than statically configuring IP addresses. But we would still use static configurations with other devices in the network, like for example the switches, and if we have configuration ports in the switches, or routers and other servers and things like that, where sometimes we may need to have static IPs there. We may need to have always a static fixed IP allocation for those, and in those scenarios we would use static allocation. But in other cases we would default to dynamic IP allocation. Then another sort of thing that you may encounter when we have networking devices is many networking devices will have various indicator lights on those devices, particularly if you look at Ethernet RJ45 cables, and if they connect to a particular port, they may also have additional indicator lights indicating various things about the status of the connection. Sometimes they may indicate the speed, the operating speed. They could indicate the status of connectivity. They may indicate whether there's active network activity or the connection is there but there's no activity happening. So there are various reasons. These type of indicator LEDs also you may find in routers and other devices. And so these are some of the additional things that we would encounter around routers. And again, this is mainly when we are dealing with the actual physical routers and when we are physically looking at the physical connections and so on. But that's one of the things that I want to sort of establish at this point as well. Our main focus is not particularly about physical devices in this case, because networking is no longer that at your level. Because, like, as graduates who will be graduating with in a networking specialization, your focus will really be the networking devices, installation and maintenance of networking devices, or even structured cabling and things like that, but rather more on the side of high level configurations, topologies, VPNs, and things like that. So, but it's still good to have an understanding of how the underlying physical devices work. And then many of these devices, such as switches and routers, will also have additional access possibilities to connect to them. So they could have serial ports, USB connections. They could have console connections. So there could be a number of ways that you can connect to them. Um, um, and most likely these days, the preferred way of connecting is through either SSH or some form of web portal, or like web type connectivity through HTTPS. So this is to get into the device and configuring the devices. So you will look at some of these things in your lab activities from next week onwards as well. So connecting to devices, configuring them, and all those things will be part of your lab activities. And so another thing that we will come to look at in this course is we will also look at switching in a bit more detail. And when we look at switching, again, there's no need to have an IP address allocated for a switch, because switches are essentially, they will keep on forwarding packets back and forth without any need for them to have an IP address allocated to them. But from a management point of view, from an administrator's point of view, we would sometimes allocate an IP address for these switching devices, for switches, so that we can again connect to them through telnet or SSH or one of these ways, and then establishing an administrative connection to manage the device. And we could possibly, again, we will discuss about VLANs later, and we can possibly have these, all the network administration paths in one VLAN, all the user connections in other different VLANs, and there are some approaches like that as well. Again, we will discuss them in more detail later in the course. So this is something that you may be familiar with from your understanding of network layers, or the layered network connectivities. So different layers in the OSI architecture. So when we think about routing and switching, we can look at these devices operating at different levels. So Normally, when we say an end device like a computer, there we would start at layer 7 and we will go into the layer 1. And then if we are encountering a router, the router will come up to layer 3 and routing and we'll go back. But if we are having a switch in between, normally switch will operate at layer 2. So when we say router switching function, we are talking about layer 3, the switching happening at layer 3, where the information about the IP address is used as part of the decision making. Whereas when we talk about layer 2, it is about the MAC address being used as part of the equation. Again, we will these are again concepts that we will be revisiting in more detail later in the course. So some of the basic things that we will do when we are doing routing, some of the decisions that we will make when we are doing routing are about how we make the decision in terms of when connecting to a network. So again, we will go through a process of decision making, and we can differentiate between a few different things. One is directly connected networks. We will be directly connecting to networks, and we will know about that. So for example, if we have a router, so if we have a router and the router already knows about 2 other networks or routers it is connecting to, and it knows about other network devices or networks in the through that router, through those routers. So these those ones we will identify as remote networks. So the directly connected networks are the ones that are directly connected to the router that we are discussing. The remote networks are the ones that rather are connected to the routers that are connected to this router. And then we will also have a scenario of what is known as no route determined. These are routes, or these are destinations for which we don't know how to get to that network. So based on these different scenarios, we will make different decisions in terms of our routing. So for example, when a packet arrives at an interface, it will search for the routing table to see if it has a match. And then if it has, based on the destination address, it will look up the destination address and the subnet, and it will make certain decisions. If it is directly connected interface, it can directly forward the information. If it is not directly connected, because it belongs to a remote network, it knows it can forward it to that remote network. If it is also not that, but there is another default gateway can forward that. Normally, if it is an ISP connection, so normally these things will forward it to the ISP network. If it is none of that, the packet will be discarded. So for example, in your home network environment, most likely what will happen is it will come to this point. Say for example, if your computer is trying to connect to my computer, that your router will not know anything about my network. It will not be even considered as a remote network, but it will have a default gateway to the internet service provider, and then through the internet service provider, through the gateway of last resort, it can reach the outside networks that are not known to the router. So this is again a simple overview of how routing decisions are made. And when we are talking about routing decisions, this is where we will also talk about routing tables. So the routing tables are the collection of information where it will connect, it will collect all the information about the networks that it is directly connected to. Say, for example, in the case of this router, it has two directly connected networks. So this 10.0/24 network and this 11.0/24 network. So these two are directly connected network. So the routing table will have information about that. Then it will also has a connectivity to another router, and through that router it has two other networks it knows. And then routers will have certain communication protocols that they would use to exchange this information. So this is something that we will discuss in more detail later. But routers will exchange this routing information and will update each other's routing tables. So each of them will end up having all the information about, say for example, router here will learn about the remote networks through the other router, and this router will learn about the other two remote networks that can be reached through router 2. So all of them will collect this information and then use that information to forward packets onwards based on where they need to send that to. So that is what we would identify as next hop for a destination. Say for example, if a packet comes from this network router and the destination is here, then the routing table here would identify that as the next stop is always this router, and that router will figure out what to do with that. So it doesn't need to know anything further beyond that point. It needs to know what is the next point to forward to, and after that, that router can decide what to do beyond that point. So that is essentially how routing tables will be used. And then with routing tables also we can have two different approach of approaching or constructing our routing tables. One is known as static routes. So static routes are we go and configure all the possible routing possibilities within the network. So everything is manually configured. We can identify what is the best ones that we want to include, what is the best path, all the calculations we will do, and then we will do the configurations in terms of updating the routing tables appropriately at each of the router. So it has the advantage of security, so we know what we have configured, so we know what are the connectivities that are possible, and we can configure that in a manner to ensure certain resources are prioritized and things like that. And everything is in our control. But the problem with static routing is it can be very inefficient when it becomes a larger network. For smaller networks, it is functional, and in some cases it could be even preferred. But for larger networks, static routing may be very inefficient. So in that case, when we have much larger networks, we will have what is known as dynamic routing. This is where the routers will have certain protocols that they can use to talk to each other, and they will use these protocols to discover information about other routers, other networks connected to the other routers, and then collate all this information and create an updated routing table, and they will keep on updating this table if anything changes in the network and all that. So when we have a larger network, dynamic routing approach would be much more useful, and in terms of a usability point of view, and for efficient updates of the information and things like that. These two, static routing and dynamic routing, we will discuss them in much more detail in the latter part of the course as well. Um, Actually, the those are two topics that we will actually start discussing first. So in the next 2 weeks, we will talk about static routing and then dynamic routing in more detail. So, with that, that is a brief introduction to the various topic areas that we will be covering in this course. And also, we didn't touch on certain topics as well, like VLANs and access control lists and DHCP. We mentioned a bit. Network address translation and few other topics also will be covered in the course. So, as I said, when it comes to grading and other aspects, we will discuss them briefly as well now. So, you will have some lab practical activities, and you will have to do some submissions for those. And you will possibly have some quizzes or assignments, and then exams. So all of these things will largely depend on what happens around us in terms of the mode of teaching, where we are meeting throughout the semester, um, and based on that, we will have a slightly different allocation of marks for different components. If we go with an online mode, there's likelihood that we will have less marks for the final examination and more for other components. Uh, Whereas if we go with if there's a possibility that you are coming back to the university, there may be again it will depend on when that happens and all that. Nobody Yeah, but that is roughly the type of assessment types that we will have in the course. Then about the lab sessions. So in this semester, the lab sessions would be conducted by Mr. Surat. So he's a new lecturer at our department, and he is also a certified Cisco instructor, and now we will use the access that we get as a network academy, and we will conduct practicals, lab sessions that way. Um, he will start the lab sessions from next week onwards, and weekly they will follow after the lecture hours. So normally we will have a 1 hour of lecture, a bit more than an hour, depending on the topic that we are discussing. And after that, there'll be another couple of hours, like the rest of the time will be for the lab sessions. And he will again on we will post all the necessary information on LMS, whether we will use the same Zoom links and all the other relevant information. Some students do not have access to LMS course page after. Those who have any such access issues, can you send me an email with your index number so that I can easily follow up that? I'll check that and I'll give you an update after. So that's that. And so as always, you have the LMS. You can find some of the previous course slides, and even recorded video lectures are also available. And you can email me. Like if there are anything that you need follow up from me, it's better to email, so I will get back in an orderly manner. But if you need some quick clarifications, you can give me a call or send me a message. Um, so that's about it for today with the introduction to the course. And as always, if you have any questions or any concerns, always ask early. And any questions also you can ask during the class or after the class. That would be a good way for us to go on with a more interactive learning environment. So are there any questions or concerns at this point? If not, we may conclude for the day, and we will again continue next week, same time. And next week you will also have the lab classes as I mentioned. So all the information will be made available via LMS. So thank you for joining, and actually one more thing, for the lectures I didn't particularly look at the attendance or anything, but for the lab activities your attendance would be essential, and if you have any issues regarding that, then you will talk to us and sort that out. Otherwise, because participation in lab activities will be the way that you get marks for your that part of your assessment component. So always keep that in mind. So that's all for today. Thank you for joining, and see you next week.